Okay, so we've been working on some optimization problems, and with a one-dimensional optimization problem. So if I wanted to maximize choosing x, f of x, we know exactly what we need to do. I need to get the necessary condition that the derivative is equal to 0. And then we noted that as long as this function is strictly concave, that necessary condition is sufficient. I know that the solution to this gives me the maximum, right? It's only got one hump, and that hump has to occur at the maximum. So the sufficient condition was that f of x was concave, and that could be determined by taking the value of the second derivative. So when the second derivative is negative, the derivative is a decreasing function. So once that derivative hits 0, it has to start becoming negative then after that. Why? Because it's decreasing, right? It's hit value 0, and it's only going to get smaller from there. So in the one-dimensional case, that's pretty easy to figure out. But what do we do when we have a function of two variables? When I have a function of two variables, what does it mean for the function to be concave? So it's a little bit harder to visualize in 3 dimensions, but I'm still looking for a surface that has a peak, right? So a nice concave surface has one well-defined peak and not a bunch of little peaks all around. So what does it mean for a function to be concave? So one thing, so the second derivative, by the way, so f1 is the partial of f with respect to x, f2 is the partial of f with respect to y. So I talked about that in my previous video about my notation. f1 is the partial with respect to the first argument, f2 with respect to the second argument. So then I can differentiate again, and f11 is the partial with respect to the first argument twice. f22 is the partial with respect to y twice. And then I could do a cross partial. So f12 is the partial of f with respect to x and then with respect to y, right, if it exists. And we'll do some examples where we might have this be the case. So I guess, we could do f of xy is equal to xy squared minus x squared. Okay, so there's some function. First derivative, f1, is simply with respect to x, y squared minus 2x. That's the partial with respect to x. Now I can differentiate that again with respect to y. That's the f12. Now I'm taking the partial of f1 with respect to y. That is going to be 2y, because the x term in that partial is constant. Okay, so I can, take as many derivatives of these as I want to, right? So every derivative itself is a new function of the two variables, and I can partially differentiate that with respect to any of the variables. And this notation tells me exactly what partials I'm trying to compute. Okay, so why do I care about that? Well, to be concave with a 3-dimensional function, so it's got 2 inputs and the 1 output, we're going to require negative second derivatives, right? So with respect to the same argument, the partial of the f double prime of x and f double prime of y, right? Those both have to be negative. Now, this isn't going to be quite enough to guarantee me concavity in the 3-dimensional function. So we have to do one more check which is that f11 times f22 minus f12 squared has to be positive. Okay, so maybe at some point I can put up a video or something in class that kind of walks through a little bit of where does that come from, right? So where in the world does this condition come from, this last one, that tells me anything about concavity? The first two make sense with our intuition from a single variable. So we have to think about the second one eventually here. Okay, so if that's true for all of the x's and y's that are relevant, then my function is concave, and setting the first order conditions equal to 0 will be necessary and sufficient. So if true for all x and y, then the max is at f1 equal to 0, f2 equal to 0. If I can solve that system of two equations and the two unknowns, x and y, I'm guaranteed that it is a maximum of the function. So in terms of convexity, if I'm doing a minimization problem, I'm going to flip all of these inequalities to guarantee me sufficient conditions for a minimum. And we'll probably cover some minimization problems here in the next couple of weeks. Okay, so I thought it would be interesting to look at our profit function that I just did in the last video and verify that it is in fact concave and under what conditions it's concave. So it's illuminating because it shows us that if we use beta equal to 1 minus alpha, our function is not going to be strictly concave, which helps us understand why we were not able to really find a maximizer, right? The system of equations that we had in the first order conditions, we couldn't quite solve. And the reason for that is that our function was not concave. So we were not guaranteed to find a maximum. In fact, the function in some sense was linear in one dimension, which is what made it difficult. So our profit function of capital N labor was z k to the alpha, alpha beta minus rk minus wl. And I want to just verify our conditions for concavity. So I need P11, P22, and P12. All of these second order partial derivatives. So P1, derivative of profits with respect to capital, was alpha z k to the alpha minus 1 alpha beta minus r. Differentiate that again. P11 is alpha times alpha minus 1 z k to the alpha minus 2 L to the beta, and the r is gone. So notice, as long as k is positive and L is positive, which they have to be, I can't set negative capital and negative labor, as long as alpha is between 0 and 1, the second derivative is going to be negative, right? So alpha times alpha minus 1 will be a negative number as long as alpha is between 0 and 1. So we can do the same for the second argument. Differentiate with respect to L now, partially differentiate. And I get a similar condition. And I differentiate that again with respect to L. And I have basically the same thing. I need capital and labor positive, which they have to be. And I need beta between 0 and 1 again. And that will guarantee me the second derivative is negative. Now, we have this last condition. And to do that, I need P12. So I need to differentiate this now with respect to labor, the second argument. So that is going to be alpha beta times z, k to the alpha minus 1, L to the beta minus 1. And then I'm going to square it. I'm going to multiply the other two together, and we'll see what in the world that we have here. Okay, so what I need to check then is that P11 times P1 times P22 minus P12 squared is positive. So first, what is this? Well, when I multiply those together, I get alpha times alpha minus 1 z, k to the alpha minus 2, L to the beta times beta times beta minus 1 z, k to the alpha, L to the beta minus 2. So if I simplify that, I get alpha, alpha minus 1, beta, beta minus 1, z squared. I now have k times 2 alpha minus 2, which is 2 times alpha minus 1. Same for L times 2 times beta minus 1. So that looks like a big mess, right? And in fact, it is. Now let's square P12. That's a little bit easier. So I've got alpha squared, looking here, beta squared, z squared, k to the 2 times alpha minus 1, L to the 2 times beta minus 1. And now I'm going to subtract these from each other. And it's a mess, right? So I'm going to kind of skip a step. And you're going to have to kind of write this down and verify it. But notice when I subtract, I've got a common term between them. So when I subtract these, I've got z squared, k to the 2 alpha minus 1, L to the 2 beta minus 1, times alpha minus 1, beta times beta minus 1, minus alpha squared, beta squared. All right, so it's a mess, right? Alphas and betas and nonsense everywhere. So how do we make sense of this? Well, all I want to know is whether or not that is positive. That's my goal. If that's positive, then we know our function is going to be concave because both of the double partials were negative. So when is this positive? Well, this first part is always positive, right? K is positive, L is positive, Z is positive. Well, and Z is squared. So that's definitely a positive number. So it just hinges on this being positive. So I'm gonna write this out. I need alpha times alpha minus 1, beta, beta minus 1. That has to be greater than alpha squared, beta squared. Right now, how do I know that? Is that I know for sure that alpha and beta are less than 1, greater than 0, which makes this first term positive. I've got 2 positives times 2 negatives. That will be a positive. So if I divide by alpha and beta, what do I have? I have alpha minus 1 times beta minus 1 greater than alpha beta. So if we multiply that out to verify this, I get alpha beta minus beta minus alpha plus 1 has to be greater than alpha beta. So I can get rid of the alpha betas, and I'm just left with minus beta minus alpha plus 1 greater than 0, which tells me then that 1 has to be greater than beta plus alpha. So as long as beta plus alpha is less than 1, my function is going to be strictly concave. So notice we were in trouble with the version that we were doing before. If beta is equal to 1 minus alpha, that's not going to be true because beta plus alpha is equal to 1. My function isn't going to be concave. My first order conditions won't necessarily be sufficient. Okay, that's certainly got to be enough with the exponents and the algebra for today, right? So do your best trying to follow along with this. I have in the homework an example with numbers. So you have a specific beta and alpha where we verify that this condition is true. So it's a little bit easier in the case where we have alpha and beta than in this general case, but hopefully this gives you some insight into how to tackle that problem. So I appreciate you bearing with me through this eyesore of a problem. But if you can handle this one, you can honestly handle any problem in economics.